Hey, hi guys. Yeah, so today let's keep solving my preserve doing my lecture for the undergrad advanced analysis. Yeah, so we just finished the series and the basic topology part. Yeah, so we follow the routine and apostle. So after we talk about the sequence, then we should talk about the continuity and the differentiation. So most of them are come from the routine and the apostle, and I'm not 100% follow it. I just say what I think is important and only highlight the theorem and give the proof. So I don't talk about examples. I seldom talk about. Okay. Yeah. So this is apostle. Yeah. Tongue apostle, right? Tongue apostle. Okay. So hope you guys subscribe. Yeah. So today let's go about continuity. Okay, so now we can talk about continuity in the metric space, right? Because previous we talked about metric space. Okay, so let's say we have x and y, they are both metric space. Right, so studying mathematics is good because you can say everything 100% rigorous. So x and y metric space. Let's say you take some subset of E, and so I map E into Y, right? So it's just let's say I write f of x approach to Q as x approach to P, or yeah, basically this is just notation. So some people, so usually I will use this, right? So if, so now this is just definition, right? Definition. So if I say x approach to p, f is b equals q. So in the general, in the calculus, you use epsilon delta, right? And now it's metric space, so we can use about epsilon delta. And after that, we will talk about in the general topological space, how do you define the continuous? So if for all epsilon greater than 0, if there's a delta greater than 0, so when your dx and the p where you have a distance, right? So notice that this distance in the x, right? So in the space dx xp less than delta, and it will imply that dy f of x and q less than epsilon, right? So compared to your calculus, this part is x minus p less than delta, and the f of x minus q less than epsilon, right? So this is the R1 version. If you do the RD version, you just change this absolute value to the Euclidean norm. Okay, so yeah, so let's go ahead. Okay, oh, by the way, so for epsilon, yeah, so this is for epsilon greater than 0, there is this delta such that when dx xp less than delta greater than 0 for all x in the E, right? So we only care about a subset of E. And if we have this, then we say that so we just say that, yeah, so this is just the definition of the definition of the limit. Okay, so definition of limit, basically when x and the simply say in words is basically when x and p close enough, then if f of x and q close enough. Okay, so now we give a theorem. So this theorem says that the same definition. Suppose you get limit x approach to p it equals to q if only if there exists for every sequence. So remember we have an idea of sequence, right? So if we're sequence in E, if p is such that Pn not the same as p, and the limit n goes to infinity, Pn the same as p. Let's say for Pn in E such that Pn equals so let me just say this. So this is what we define, right? For each Pn in E, limit f of Pn n goes to infinity. So now we change. So now this is the definition of a sequence, right? Equals Q for every Pn satisfy the first one is Pn. For every sequence satisfy the first condition, these two conditions. The first is Pn not the same as P. The second is that the limit n goes to infinity, Pn equals to P. Okay, so yeah, this is the definition. This is the theorem. So this just says that when x approach to p, the limit exists means that you can choose any sequence. You can choose any sequence to approach to approach. You can choose any sequence Pn to approach P. So you can choose any sequence Pn to approach P, and for every sequence Pn approaches to P, the limit Fp. So if you view as Fpn as another sequence, then for this sequence limit will be the same as Q. Okay, so this is just say that saying words, right? So just intuitive is correct. Okay, so we need to get a proof. Okay, so let's prove these directions, right? So let's say we have this, and we pick up P and satisfy this equation, this condition. Okay, so if we have this condition, then for epsilon greater than 0, right? For there's a delta. So delta that what when the dx xp less than delta, then you have dy f of x q, right, less than epsilon, right? So here's it. Okay, so now we know that the limit Pn belongs to P, right? So that means for these let's see, for this delta, right? For this delta, right? So for this delta, there exists n, right? It belongs to integer such that when let's say this is n bar, when n greater than n bar, the Pn and the P, right, is less than delta. Right? For such delta that I can choose this, right? Because this Pn approach to P, but this is x. So sometimes I'm lazy, so sometimes I don't write x. Okay, but it's obviously this should be x. So when I have this, then I definitely have this, right? So which tell you that because Pn now is less, Pn satisfy the condition, so we have this f of Pn q less than epsilon. Okay, so write down if you skip this, right, if you skip this sentence, then what you get is that for all epsilon greater than 0, there is n greater than n such that fp and q less than epsilon, right? You can skip all this, right? So this proves that the limit n goes to infinity, f of p and approach to q. Right, this become a definition of the original or if the original sequence. Okay, so let's say another direction. So another direction is hard to prove. Let's maybe do some you need to prove by contradiction. So suppose the limit go this, right, as approach to p is not converge to Q. Right? So basically, you just suppose that the result is wrong. Okay, and you try to prove it. Okay, so that means what? There exists epsilon greater than 0 for all delta, right? For every delta, right? And there exists x belongs to E, such that what? So just revert dy f of x q greater than epsilon, but dx x where p less than delta. Okay, so this is just the negation of the original sentence, right? Since these do not converge to q, so that means there exists epsilon, right? For every delta greater than 0, there always exists point x, right? This x is dependent on delta such that dy f of x greater or equal to q. But you can, so basically when x approach to p, however close, right? There exists some epsilon that however close you cannot approach to it, right? So there is a bound that you cannot approach to such point. Okay, so suppose this is true, right? So this is exists epsilon, right? But for every delta, so I can choose delta to be 1 over n, right? But this sentence means that there exists epsilon such that delta is 1 over n. So so this you can let n grows to n. You can let, right? You can let n goes to large infinity, right? So when let epsilon n goes to infinity, then this sentence will imply that limit n goes to infinity, f of Pn will not the same as Q, right? But this violates our original assumption. Okay, so just a stupid corollary. I think this corollary is simple, so I don't want to prove. So basically, if the limit exists, then the limit is unique. Okay, so this proves why this is corollary, right? Because we already proved that if the sequence, if the sequence converges to some point, that point must be unique by definition. Almost by definition. Okay, so now we can define two functions, right? So let's do some very simple definition. Right? This simple definition is so simple that right, if you have x belongs to y and g x belongs to y, then you can define addition. Okay, so usually it's not the. If you want to define addition, you need to make sure that there's addition in y, right? So now suppose we focus in a function from some space to Rk, right? Then in Rk there's a addition, right? So I can define the addition of the function, so f plus g on x can define to be f of x plus g of x, and there is this c of x times this, then become so this is the define function times a constant x on x is c x on f of x, right? So this makes the function become a vector space, right? So yeah, all the function become a vector space. Okay, and also you can add the product, right? So let's define this. I think due to this, then this become a ring. Okay, commutative ring. Okay, so theorem that I skipped the proof because I think just follow the same as the series, right? So the series say that if a and b and converge, then n plus b and converge to a plus b, where a is a converge of a and b is the converge point of b, and then b and converge to ab, a and divided by b and converge to a belongs to b when b and non-zero, b is non-zero, and also a minus b and converge to a minus b. Yeah, so this is the simple exercise for the series. I think you just use the epsilon delta. Okay, so from this you can easily prove that when x approach to a, f of x plus g of x, so this guy become f of let's say p plus q, where p is a limit point of f, q is a limit of q, and also the product, let's say you approach a and f of x, g of x, where it become p times q, okay, and also the minus and the division when the denominator is non-zero. Okay, simple proof. Define a continuous function. Okay, so f also a matrix space, and you suppose you only focus on some subset, and then we say that if f is continuous at p, if limit x approach to p, f of x is the same as f of p. Okay. Yeah, so this is the definition. Okay, so you see there is a limit the same as the points value, which means the continuous. So the condition is that so if f want to be continuous at p, then f must define at p. Okay. Also there is a remark. So if p is an isolated point, which we just mentioned that in the topology, right? So p is an isolated point means that for all epsilon, right, there's no such point. It exists the epsilon where there's no other points, right, which can approach to f. So at this case, right? So at this case, f is automatically continuous at p. Okay, the reason is that we will say for all epsilon greater than 0, right? But actually, you can, right. So for whatever epsilon you choose, right, you can pick delta to be greater than 0. Oh, sorry, I just clicked something. You can choose delta to be greater than 0. Right. So at that case, right, your delta your dx xp where less than delta is only the point is only x equals to p, right? Then you will have this d f of x f of p, which is just equal to 0, right? Yeah. So for I think for isolated points, we just say of f automatically continuous. Okay. And there's a theorem that I don't want to prove. I think it's simple. So suppose that you get 3 matrix space, and let's say f is defined to be x mapped to y. Suppose you only care about some subset e mapped to y, and also suppose you have g, right? And the g map y from z, right? Suppose g map y from z. And suppose f is at some point p, which is converge, which has a limit, and the g has some limit. Then the g times basically f. What I want to say is that f is continuous, g is continuous. Then g circle f, right? G circle f will should be e from z is continuous. So basically, the composition of the continuous function is continuous. Okay, so proof just okay, so let's prove. Okay, so let's say for epsilon greater than 0. Okay, so let's prove converge at this point p, right? So suppose this is p, right? P belongs to this, and f of p belongs to y, right? And g is a continuous function. G is continuous at f of p. So by definition, so g is continuous at f of p. And then we want to prove that g f p, this guy, right, as a composite function is a continuous at p. Okay, so by definition, I pick epsilon greater than 0. So we know that g is continuous at f of p. Continuous. And there's this eta greater than 0, such that you care about g of y and g of f of p, right? Let's say this is z less than epsilon if d of y, let's say y and f of p less than delta, less than eta, right? By definition, and then y is belongs to f of e, right? So this is just the definition say that. So this definition just write down this. And you know f is continuous at p, right? So f is continuous at, so now I can control this term, right? So f is continuous at p. So that means there exists the delta greater than 0, such that you can control this term, right? F of x, y is f of x. This guy f of p less than eta if dx xp less than delta, right? And x belongs to e, right? So you read the words basically for epsilon greater than 0. There's a delta greater than 0, such that when x less than delta, when x and p distance less than delta, then you will have this, right? So y is just f of x, so this is just f g circle f with x, right? So you return words for epsilon greater than 0, there's a delta, and then when x and p less than delta, then the final result less than epsilon. So proof done. Okay. So this is just the word. Okay, the theorem. I suppose f x mapped to y is continuous. So let's just write the conti. If and only if f inverse v. Okay, so this is the very important results. Okay, so f inverse v is open for all v open in y. Okay, so this is very, very important. This is the probably the most important theorem in the continuity. Okay, because we will use this idea to define a continuous in a general topology. So in the general topology, there's no distance. We only have an open set. So one can define all continuous function by saying that the inverse map of open set is open. So this f of inverse v means that the preimage of v. So this theorem say that if x mapped to y continuous means that the inverse y is open for all v open in y. Okay, so this is probably the most important part. Okay, but now we're working in a metric space, right? So hopefully the proof is easy. So proof. Okay, so what we need to say? Okay, so let's say proof this direction. Okay, so if somebody want to show f inverse y is open, that means that we need to prove what? We need to prove that the f inverse y is any point in the f inverse y is an interior point, right? This is the definition of open. Okay, so let's see, right? So we need to do this. So let's see. Let's see. Okay, so if p says p belongs to x, and then we have f of p, right, belongs to v, and the happy thing is that v is open, right? So v is open. Right. So by definition, right, there exists epsilon greater than 0 because this guy is open, right? So if you draw a picture to help you, so f of p, so you can it is epsilon, right? It is epsilon greater than 0 such that what? Such that d y f of p x less than epsilon. If this thing happen, means that so now every x belongs to v, right? So if this guy then every x belongs to v, then so basically if x satisfy this condition, then every x will inside v, right? So this is because this is f of p is a open set. And plus what? So now f is continuous, right? F is continuous. So that means what? There exists a delta greater than 0, right? So such that, so remember f is continuous means that for all epsilon, right? So now I pick a particular epsilon such that this small ball falls into v since v is open. So if so f is continuous, right? So I can pick up delta greater than 0. So when dx and x, let's say p. So when dx, maybe I use this y. If dxx less than p less than delta, let your dy y, right? dy y f of p will less than epsilon, right? So this dy y just f of x, right? By condition, by the f continuous. So you return in the words, you just say that when somebody choose epsilon, right? You can choose the smallest enough delta, such that when this condition holds, then you satisfy this condition. So you satisfy this condition, right? Okay. So what you're saying is that when dy y f of p, right? So what you're saying is that there exists the delta, right? And this is epsilon greater than 0, and you can find delta such that when delta dx x and p less than delta, your dy y f of p less than epsilon, right? So which just saying that you just show what? You just show that when your x very close to p less than delta, then you can make your image falls into this ball, right? You can make your image falls into this ball. So just saying that y belongs to v, just y is f of x, right? So f of x belongs to v. So just saying that x belongs to f of inverse v, right? So what I'm saying is that so what I'm saying is that every point which is close enough to p will become the f inverse of v. So this means what? This means the f of inverse v is open, right? So f of inverse v is open, right? Okay, and then conversely, so conversely, suppose f of v is open, so it's open in a larger space, in the original space x, right? So for every right? For every v open in y, then what? Then let's say you pick p belongs x and epsilon greater than 0, and you define v to be a set of all the y belongs to y, such that let's say dy y f of p less than delta epsilon, right? So you choose a set which is a v, and you see now you see what? Now this is original in y, right? So in this space, which is so this is open ball, right? So v is open, right? V is open. So by definition, by your results, the f inverse v is open, right? So f inverse v is open. Okay. So since f of inverse v is open, right? F of inverse is open. So this means that there exists the delta greater than 0, right? Such that when x there exists delta greater than 0 when x belongs to so there exists delta greater than 0 such that when x is close to p, right? Then all the points will force into this set, right? Because f inverse is open. But this is just saying that when x and p are close enough, then dy y f of p is less than epsilon. Okay. Yeah. So this just like change your word. I think it's not so difficult. Okay. And there's a so there's another theorem which is obviously just a corollary. So another says that f map x to y is continuous if and only if f inverse c is closed for every c. So for c is closed in y. Okay, so the proof is basically simple, right? Because the closed complement is open, right? So okay, so the reason is just if you were supposed to take any set E and you do the complement, which is just f inverse of E, and then take the complement. Okay, so if the original C is open, then its complement is closed, right? So, and if your original basically you just change your C complement to be open and then apply the previous results. Okay. Okay, so yeah, and the theorem is so simple. So if average is continuous, then your f plus g is continuous, f minus g is continuous, divided by g is continuous. For that point, g is non-zero, f minus g is continuous, as f composition g is continuous. Okay, so proof is just same as the previous one. So corollary, it should be simple. Okay. Okay, so let me define a final theorem. I think it's enough for talking. Continuity is simple. We use another video. We'll finish this. Okay, so this theorem says that suppose you have a function f of x, which is a composite function, f1, f2, up to fn, and I should say that so each fi should be mapped to, let's say I say map ex to r. Okay. So this large f should be the composite of a small function. The first coordinate f1, f2, up to fn. So this is x mapped to rk. Okay. So theorem says that so f is continuous, right? So f is continuous should be what? So should be respect to the norm, right? So respect to the norm of Rn, if and only if each component is continuous. So each component is continuous respect to R, right? You respect to original R. Okay, so this proof also simple. We just need to suppose we can bound this, then we should be able to bound this, right? So simple. And the reason is that what? The reason is that I suppose you're f of j, so you pick out some coordinate f of j minus f of y, right? You try to bound this, This can be bound, right? This can be bound by the all of it, right? Because there's maybe another code, there will be another component, right? So the single component distance will be greater or equal to that. So that means if this guy continues, that means you can bound the least term, you can bound this, and you can bound this, so you bound this. Okay. Conversely, this is just the summation of this, right? Take a square and I from one and take a square root, right? So suppose you can bound this each term, you can bound this. So the proof just this sign and this sign. So these two are the proof. Okay, so yeah, so next time, I think next time we just talk about continuous and compact, and also there's a thing called upper continuous, but I think it's not so important. Yeah, so we can quickly go through this simple analysis. Okay, see you guys next videos. Bye bye.